Hello, and welcome to the second joint webinar between Expedera and Andes Technologies entitled Designing for the Future, Important Considerations for Specifying a Main Processor and AI Accelerator. If you missed the first of our webinars, you can find information on how to access that within the webinar. My name is Paul Karazuba. I'm the Vice President of Marketing here at Expedera. My background is in a variety of semiconductor technologies, including products and IP in computational and optical imaging, high-speed interfaces, and silicon device security. Prior to Expedera, I've worked in marketing and product at PLDA, Rambus, QuickLogic, and a number of others. John?
Yeah, thank you, Paul. My name is John Min. I'm the Director of FAE at Andes. I've been around processors all my career, CPUs, DSPs, and custom ASICs. Prior to joining Andes, I spent the last 20 years at Sci5, MIPS, and ARC, the CPU companies in various roles. Before then, I worked at consumer electronics companies like LG and HP. Next slide. So let's just dive right into how we do as a CPU company approach AI. So the host offline probably does the training and main service model. And what CPU does, or consumer devices does, is it runs the runtime libraries. For example, as a baseline CPU, runs the reference kernels. It may not run at the real time. It may run at different time. To accelerate that, we use some advanced libraries, software that with advanced cores that could accelerate AI performance. Or we rely on companies like Expedera to supply a neural net specific hardware engine. Next slide. So one example of the AI fundamentals, we don't support the entire AI models. What we support is software that accelerates different functions of the model. So for example, we have activation functions, math basic functions, concatenation, convolution, and other functions that you can use as a building block to build your AI runtime kernels. Some examples, we do expect acceleration of about 6 to 10 times using the DSP SIMD instruction set, the P extension, and RISC-V. When using V vector extension and RISC-V, we could get acceleration up to about 50 times. Now, this isn't in the class of acceleration that Expedera, a dedicated engine, could provide, but depending on your usage model, this may provide enough function for some of the lightweight AI kind of computations. Next. So here's one example, Cipher 10 neural net imaging model. So as we use the fundamental building blocks to build the Cipher 10 neural net model, and you could see the acceleration. So the DSP, that's when we use the DSP, and using 64 DSP and AX45, we could accelerate the performance about 5 times over a standard processor that are used today. What does that mean? We could finish 5 times faster, 5 times better frame rate, or we could finish 5 times faster and go to sleep so we could save power. So we're CPU, we use software. Next slide. And where we could use this CPU is fundamentally the CPU is required in most intelligent processing chips. So we start with a simple processor like our N22, N25, or N45 to manage the CPU, do the secure boot, or manage the firmware image that's running. Next slide. And moving on from the next point is the user interface. So if this is a device that interacts with end users, so we now have more richer processors that could run Linux or rich operating system that could give you user interface, graphical user interface, and a processor can do that. Next slide. And what's most interesting is now you have some AI workload that maybe the CPU could do it. These include the very simple image recognition, voice recognition, keyword spotting, where you do not need a really high-powered processor, high-powered acceleration engine. We do have a sort of mid-range acceleration engine in NX27V, which is the first commercially available RISC-V vector processor that could execute up to 8 or more instructions at the same time. Next slide. But one of the key challenges of doing AI, whether you're doing it as a CPU or the accelerator, it's not really the compute. Compute is the easy part. The question is, how fast can you feed that? Think of a freeway. Designing freeway or the car is the easy part. It's the how many cars could get through that freeway at the same time. Data has to get through that freeway. So we've accelerated data movement in our advanced processors by adding something called MemBoost. It's a collection of technologies that accelerate data movement. We have a data cache write around. So perhaps you have data that needs to be used again, so you put it in the cache, or perhaps you have data that needs to go out to an accelerator immediately. So we have technology to do fast writes, instruction and data prefetch. Generally, a lot of AI workloads tend to be very linear or a loop, so that if data is available linearly in a contiguous address space, we'll get the instructions and data, prefetch it so it's available to the CPU. So we're on and off the bus as quickly as possible, but we'll bring in as much as optimally necessary. Third thing we do is outstanding memory requests. So there are in CPU systems, SoCs, there are slower memories, fast memories, slow peripherals, and fast peripherals. Well, if you don't want to access to fast peripheral be slowed down by needing to complete the slow accesses. So we have out of order memory reads and writes. So this accelerates overall system performance and makes all the peripherals perform at the optimal level. Last thing we have is this is the old CPU paradigm. So do you want a von Neumann architecture which shares address and data bus? It's great to make it very compact. It doesn't use a lot of pins. So it's really nice architecture. However, instruction and data need to share that bus. Now we could completely separate the instruction and data bus interfaces and have a complete Harvard architecture where now we have twice the bandwidth to move instruction and data, and we could optimize those buses separately. What does this happen? It increases our memory performance about 3 times. And what it shows in the actual performance is memcopy routines are 3 to 4 times better, better performance. So you could really move the data in and out. So this is one way we've improved the CPU portion. The next slide will show how we do the sort of a larger SoC level integration. So one other technology we have is ACE. It stands for Andy's Custom Extensions. And this allows for me to accelerate neural network, particularly by adding instructions, adding custom ports to move the data in and out, and adding memories for temporary storage or perhaps formal storage of the data. So there are a lot of ways we've improved our processor to help in the neural network applications, whether we compute it or whether we talk to external accelerator like the Expedera that Paul's going to talk about now.
Thanks, John. So I want to address some of the design considerations that a system designer or a chip designer should take into account when looking at how they should deploy AI acceleration in their chips. So let's first start at looking at just a few of the neural networks, whether they're ResNet 50 or YOLO or UNet. There's a large variety of networks that are available, each with their own unique reasons for existing and the typical tasks. And they tend to obviously vary wildly, as you can see on the screen here. Something like MobileBERT is a language understanding network, whereas ResNet 50 is basically a connection that allows deeper networks to be enabled for things like quicker image classification, object detection, etc. And each one of these has a completely different level of complexity. You know, if you look at the number of layers or the number of operations in billions or weights or activations that are required, Each one of these is obviously completely different and is going to require a different level of performance and capabilities from your AI engine, whether it is a CPU-based AI deployment or whether it's specifically via an NPU. And let's be honest, I'm sure any designer on the webinar today would probably make the statement that traditional NPUs just simply don't make it easy for chip designers. And this could be because of the amount of DDR access that is required, the relatively poor utilization that's typically present on NPUs, or of course the PPA, the power, the performance, and the area targets. As we say here, traditional AI engines, they're generally inflexible. They require large amounts of memory transfers. This is one of the reasons for the, frankly, very high power consumption you typically find, as well as the low utilization. They're constantly shifting data around on the chip. They have poor utilization. An average AI accelerator may have utilization in the 20 to 40% range, and we'll touch on this a little later on in the webinar. And often they don't meet chip designer PPA targets, and we'll again address that. And in worst cases, sometimes they require significant changes to your existing trained neural networks. And that's not something that a typical chip designer wants to go back and talk to their data scientists about. So let's talk about questions. Questions to ask during your NPU specification. And we're going to go into detail on each one of these. We're going to worry about what neural networks are you actually running? What are your PPA targets or your constraints? And something that I think gets overlooked in a lot of specifications is when to future-proof. So let's go through each one of these. So first, let's talk about neural networks in your designs. And I'm going to use NN on the slides here, and that of course means neural network. Neural networks vary greatly. We saw the complexity and the processing required in an earlier slide when we looked at the 5 different examples. But to be fair, chip designers often don't have the choice of what neural networks they must support. The data scientists, the machine learning scientists, often in completely different parts of engineering, are the people that are determining the best neural networks to run for the desired application and placing that burden on the chip designer to support the network or networks and the level of complexity that those entail. So let's start out with a little bit of advice here. Do you know your neural networks? If so, optimize for those neural networks. That seems pretty obvious. But in some cases, you may not know all of your neural networks, and this gets to the future proofing that we'll talk about later. So our advice, if you know most of your neural networks, optimize, but definitely provide flexibility, possibly with the CPU. And do you need to support everything? And what I mean by everything is how much of your neural network needs to be supported on the AI accelerator, what can be supported in the CPU, and what does the future look like? So make sure you have flexibility in your AI engine that allows you to offload processing when it makes sense to other parts of your system. And even though we're going to talk about this later, what does your next generation product look like? And what I mean by that is, what's the value of choosing an engine that's going to scale with your needs? Certainly, selecting an AI architecture that hits your needs today is great, but if you're able to reuse all of the learning of that architecture for your next generation product, which is presumably going to have scaled AI needs, what's the value in not having to start from scratch and instead be able to take what you know and move it to your next generation? Let's touch on PPA, power, performance, and area to those of us in the CPU world. PPA specifications and constraints are typically set prior to chip design. And like the example of neural networks, they're not generally being set by the design engineers. They're being set by other parties. And as we all know, they're interrelated, but they're not aligned. And what I mean by that is you can get higher performance, but it's likely going to cost you an increased area and increased power consumption. And that may or may not be palatable in your system. And when we look at PPA and we look at AI inference engines, not all inference engines are created the same. Specifications vary greatly, and I want to examine just a single instance of how specifications vary greatly and how you really need to look into that. We're going to use TOPS as an example. So another bit of advice we'll give you in this: dig into TOPS before you make judgments. Benchmarking performance of one AI engine versus the other, it's a multi-dimensional problem. TOPS is a commonly used benchmark across the AI industry. Expedera uses TOPS, so certainly, understand that. And TOPS is, max times frequency times 2. But we'll stop right there and say, by itself, just how many TOPS an engine has is not an entirely meaningful number, especially when you're comparing one AI engine to another AI engine. You really need to examine the assumptions and the underlying method used to create that TOPS number. Some examples. When you're looking at TOPS normalized to the same frequency, many or most AI inference suppliers use 1 gigahertz as a frequency. However, others use a frequency that's a little bit faster. It gives the appearance of more TOPS. Normalized, it may not actually have more TOPS. So you want to look at that. You also want to look at what network was running. Certain networks require more TOPS, are not as efficient. You want to look at what precision was used at the data running within the network. Of course, was sparsity enabled? If you run 30% sparsity, you're going to have a higher TOPS because you're not processing as much. You really need to look at that. And let's also look at one more factor here. TOPS is a theoretical maximum throughput, but it doesn't actually factor in the utilization. And utilization varies greatly across AI accelerators. I mentioned earlier the 20 to 40% number. Now, it is fair to say that many AI engines have utilization that might be stated at, let's say, 65, 70%. However, that's generally in a sweet spot of that particular accelerator, let's say 4 TOPS or 5 TOPS. As a system designer, as a chip designer, you really need to explore that utilization number and understand how it changes depending on the TOPS that you're at. Is the utilization consistent across the performance range of the product, or are you being given a utilization number that's specific to a sweet spot and has a significant roll-off as soon as you go away from that? You also want to look at inferences per second, and that actually might be more informative, how many actual processes is taking place. And of course, you want to dig into inferences or TOPS per watt and inferences and TOPS per millimeter as well. That's going to tell you your power in your area. And let's also be fair, process node is going to have a significant effect on your per watt and your per millimeter number, as all of us in the semiconductor world know. So the takeaway from this slide, as I'd say, is when you're comparing AI engines, be sure to know all the details. Looks can be really deceiving, especially when you're only looking at one number. So, coming back to PPA, with the specification, the constraints of PPA intertwined, inevitably your final decisions are going to become a design trade-off. Chip designers need to prioritize and design accordingly. Dig into those underlying assumptions of all the specifications on your AI engines before you decide on the best one for your need. And one other thing I might tell you here is request accurate PPA simulations ahead of tape out from your AI supplier. And what I mean by that is an AI supplier should be able to tell you this is what your power, your performance in your area is going to look like given your neural network models and what your targets are. And if I may, Expedera sees our customers' PPA constraints as opportunities for improvement. Our first production customer, which we announced in the early part of March of 2022, saw a 20x increase in performance at less than half the power consumption without an increase in area compared to their prior generation AI solution. And that was because they came to us with what they saw as constraints where they had a specific area. We saw that as an opportunity to maximize the amount of performance and balancing the power that they saw in that. So again, make sure you get simulations from your AI supplier before you make a decision. And let's also talk about the future. AI algorithm development is far exceeding Moore's law. What I mean by that is AI engines at the silicon level just simply cannot compete with how fast AI algorithms are being developed and the increasing complexity of those. So a question you need to ask yourself is, how long is your product actually going to be in the market? Is your algorithm support closed at product launch? Or are you going to support new algorithms when your product is already out in the field? And how much flexibility do you require? And then once you've made that decision, you really need to look at your NPU, your AI engine, and understand how open and easy is it to support new algorithms on your NPU once that chip is deployed. And let's also look and say, are those new algorithms based on standard or custom neural networks? There's a lot of questions that you have to answer on this. And unfortunately, suppliers like Expedera are only able to answer some of these questions. A lot of really design considerations. And make sure you choose the AI engine that supports as much of your needs for the future as possible. So let's compare a couple of AI use cases which demonstrates different needs. Let's use perhaps two very different ends of the spectrum. An automotive-based AI use case, which might be for something like ADAS or self-driving, coupled with a doorbell-based use case. In the automotive world, your AI engine is running 100% of the time. It's likely running multiple neural networks simultaneously. Because of the safety concerns, because of the legal concerns, because of just the needs of the automakers, performance is going to be your top design consideration. Probably then followed by power, because of course we can't have our AI engines, making any sort of measurable dent on the electric range or the gas mileage of a car. Area, perhaps not as much of a consideration, but future-proofing, very important. As new AI algorithms are developed, as the neural networks get more precise, as they get better, you are going to want to make sure that your NPU has the ability to handle those new networks in an easy way. But let's switch to doorbells. The AI engine likely is only going to run sporadically. It may only run when motion is detected. It may only run when the doorbell is actually pressed. And it might only be running a single neural network. But in this application, power and area are going to be your top design considerations. There's likely plenty of performance in a typical NPU to do what a doorbell maker would need to do. However, the power and the area are obviously going to be of primary importance, whether it is battery powered, and of course the form factor of a doorbell is obviously much different than the form factor of an automobile, and a chip size that might be okay in an automobile likely is not going to be okay hanging off the side of your house. And in this case, future proofing is likely not as important. A doorbell may be shipped without the ability to do any upgrades to the neural networks, and that might be perfectly acceptable. Again, this is a decision only the chip designer and the chip company can make. So let me close with just a little bit of an introduction to Expedera, our product and our company, and then I'll pass it over to John. Expedera's architecture is extremely flexible. Our AI can be optimized for application-specific needs, whether it would be, a doorbell or a car, the two examples that I gave you. The minimal memory footprint. We require very few, if any, read and writes to external memory, depending on the particular configuration. Obviously, this is going to reduce your power and your costs while increasing efficiency. Scalability. We talked about this on the first of these webinars. Again, the link for that is available within the webinar here. Expedera's IP scales from 10 gigaops to 128 TOPS from a single engine, and of course to petaops if multiple engines are deployed. Now, high engine utilization. Our AI Accelerator performs at the 70 to 90% utilization range across our entire performance range. not just specific sweet spots. And I would be more than happy to back up that claim. You have questions, please reach out to me. And of course, Expedera has the industry's leading power performance area, and that is verified through third parties. And there are white papers available as attachments to this webinar that show that. And we would also be more than happy to point you towards third-party data that shows that. And finally, from my side, just a quick overview of who Expedera is. We're a Silicon Valley-based Series A startup, and we have applied our networking principles of packets to AI accelerator inference technology. You know, I've mentioned our patented scalable neural engine IP. We have unsurpassed inferences per second per watt, inferences per second per millimeter squared as well. We are field proven, so even though we are a startup and even though we only came out of stealth mode a short 11 months ago, we are currently shipping in a leading consumer device from one of the world's largest manufacturers, and we're silicon proven in multiple leading edge nodes. We are made up of an experienced team of experts from Cisco, NVIDIA, AMD, Qualcomm, and others, and we stand ready to address your needs. John.
Well, thank you, Paul. Well, let me give you a little bit of overview of Andes Technologies. We are a pure play CPU IP vendor. We've been doing this for about 16 years, so we predate RISC-V. However, we joined the RISC-V Foundation or RISC-V International as a founding member, and we are participating in many of the activities, and we're a major open source contributor, and we maintain a lot of the tools. We have a lot of experience, and one key note is, as of last year, end of last year, we've shipped more than 10 billion chips containing our IP. So we are, as Paul said, we are definitely field proven. Next slide. And what we have is a broad range of processors. We start with N22 on lower left, which is very small, compact microcontroller with a more higher performance microcontrollers. We do have the DSP vector line that works very well with external accelerators, whether you want to offload some work to the CPU or you want to do the entire AI workload by itself with powerful number crunching engines. And then we have application processors that could run Linux. So come talk to us, pick the right processor for your application. There's a big menu to choose from. Next slide. So thank you very much for coming to join us on this webinar. Now to some questions you might have regarding the topics we covered.
All right. If you do have a question, you can go ahead and enter that into the question widget. John and I will get to as many of the questions as possible today. And if we don't get to your question, we will be more than happy to follow up with a personalized answer after the fact. So John, first question to you. Is the top specification the same for a CPU as it is for an NPU?
Well, thanks, Paul. That's a really great question because you put a formula up. Top says max times frequency times 2. In CPU, we calculate it differently. There's a term that you might be familiar with, MIPS. So that's million instructions per second. We get multiplied by frequency and we get million instructions per second. In a way, in CPU world, instruction equals operation. I think in your world might be too. And it's important when you get some number like that, ask what it's based on. Is it the, when you say Mac, is it 32-bit Mac, 16-bit Mac? Maybe it's 8-bit Mac. So precision of the calculation matters. So for CPU side, generally it's 32-bit by 32-bit multiply times the frequency. And if it's 16-bit multiply, I would expect twice the performance from 32-bit multiply. And that's the terminology CPU uses. Paul, what is your terminology? Is it different?
It's exactly what you just said and what we said earlier in the remarks. Max times frequency times two. So there actually is an interesting question also about tops that's probably more directed at me. And let me read it here. Expedera mentioned digging into the underlying assumptions of top statements. So how does Expedera define our tops, or what is? I'm guessing the question is, what is Expedera's assumption. So we state tops based on silicon, and for our particular top statements, we talk about 18 tops per watt. In TSMC 7 nanometer at a 1 gigahertz frequency, running a ResNet 50 into 8 precision at 0 sparsity. So we try to be as specific as we can possibly be about this. And obviously that's done intentionally. And of course, as we talked about, if you change sparsity, if you change process node, frequency, et cetera, it is going to change your frequency. Next question here. I guess this one would also be for me. I've heard AI companies talk about utilization. How does Expedera compare? That's an interesting question. Expedera's utilization is 70 to 90% across the full spectrum of performance. The full spectrum performance for us is anywhere from roughly 10 gigaops to 128 tops on a single engine. And that's that same engine that's scaled to cover that entire range. And we assume, again, ResNet 50 into 8 for that as well. A lot of other manufacturers don't necessarily quote utilization. I have seen some information lately where companies have been quoting utilization of 70%, but at what they call a typical AI use case. I'm not really sure what a typical AI use case is. Certainly, I would want to dig into that if I was looking at that engine to understand, what the roll-off might be when you're not in a typical use case. So hopefully that answered that question. John, this next question looks for you. And I should also say before I ask you the question, if you do have questions, please go ahead and enter them into that questions widget. We'll do our absolute best in the time that we have. So John, for you, does an SoC that contains a neural network, a neural engine, does it need a CPU?
Generally, most chips will require some form of CPU or a state machine, at least for initial setup. So I would imagine your accelerator has some initial setup requirement, memory, you need pointers set up a certain way. So I think all the chips today will require a CPU, maybe a very small one for setup, perhaps for secure boot, security reasons. And then you get to decide whether um, the accelerator, does it fulfill 100% of my needs? Or perhaps if I put a little bit of intelligence, like data formatting, what was used to be like Indian conversion, big Indian to little Indian conversion. If those things CPU could assist with, maybe Expedera accelerator could run from 90% efficiency to 95% efficiency. So the ultimately SoC architects and designers get to decide how much CPU performance they will put in. And good thing for us is you will need some CPU. So you have to come talk to us anyway.
Sure. And, John, let me echo, Expedera's origin NPU is definitely not a host CPU. Our IP is designed to work alongside a CPU like those from Andes. So we certainly would expect there to be an NPU or rather a CPU or some kind of master processor on the same chip that our IP is integrated into. Interesting question. How can I future-proof if I don't know what the future holds? Fair enough. Absolutely. The problem, obviously, with trying to future-proof anything is there's no way to know what the future is going to hold. And as I talked about in the slides, AI algorithm development is accelerating, if you're pardon the pun, much faster than Moore's law. And it's really impossible to know exactly what the future is going to hold because there's standard neural networks, there's custom neural networks, and a lot of companies today are using custom neural networks to better accelerate AI algorithms on their devices. So if you're a chip designer and you're looking at the future and you make the determination that you do need to have some sort of future proofing in, you're going to have to, as I said, look at the networks you're supporting. Look at what networks you could be using. Look at, are they going to be custom? Are they going to be standard? And then what's the complexity of deploying those on your silicon? Is it going to be possible? What's the complexity of support, the complexity of upgrade? In Expedera's case, an overarching statement, as long as the math of that new or that custom neural network is supported, for us, it's essentially, putting new software onto a system. But that's not true of every neural engine. And certainly, there's no way that I or anyone else can guarantee that your NPU is going to support all networks in the future. So that's a question that a system designer or a chip designer is really going to have to ask for themselves and understand. You're going to have to understand what possibilities are there in the future, and how and if we are going to be supporting. So I really don't have a great answer to that question. Just perhaps some advice. And it looks like we have time for one more question. John, what options do I have to increase processor performance?
So this is where it leads to future proofing as well. So in a way, there's two dimensions. One dimension is you could always run faster for CPU. You could have 100, and we see a lot of SoCs that close timing for CPU at a couple of different frequencies, maybe at 100 megahertz, maybe at 500 megahertz or higher. So the CPU is nice, you could always go faster, but then you get other pressure like memory movement. You got to feed that CPU. Second way is to add more extensions or instructions to the CPU. And BISC-V is ideal for that. So we start with a base CPU. We could put in DSP instructions, and then we could put in vector instructions. So now CPU gets bigger, but you get to choose what you want in your CPU. Maybe next generation, you put a more beefier CPU. Or other dimension to go is multi CPUs. So a lot of AI workloads are very parallel. So multiple cores definitely help, as your Expedera cores are probably multiple executions. So increase execution units. So there's a lot of different ways to accelerate performance. In some ways, future proofing, right? You over design a little bit. Software could always make up for a change in specification. That's ideal for that. And you get to make a trade-off between performance, power versus area versus cost.
Sure. And it actually looks like we have time for maybe one more question. So let me just hit one more. Considering a system with both an Andes CPU and an Expedera NPU, how do you handle memory transactions when processing neural networks, for instance, to deliver the flexibility and future proofing of the end device? So let me answer that first from an NPU perspective. The Expedera NPU is built to have the least amount of memory transactions required. It's due to our packet-based architecture. We've talked about that in previous webinars. In the attachments to this webinar, you can find links to those. I won't go into a long explanation here, but I will do maybe a cheap plug, as we say, for those webinars and for those white papers you can find links to. But the packet-based architecture of the Expedera NPU is designed to minimize the number of memory transactions that you have to have. And that directly leads to increases in efficiency or certainly decreases in cost, because you don't need to put as much system memory in, and certainly decreases in power because you're constantly not writing back and forth between the NPU and power. And certainly, from a combined system with an Andes CPU and an Expedera NPU, as we talked about in part one of this webinar, there is the ability to offload processing of certain layers from an Expedera NPU to an Andes CPU, where it might make sense for processing sake or power's sake. John, would you have anything to add to my answer there?
Yeah. So there's two ways that we help with Expedera Accelerator. Is since Expedera Accelerator is so frugal on memory transactions, when we access the common memory, the four memory technologies I mentioned help with that. We're on and off the bus quickly, so you could have multiple agents being on the bus. Secondly, we could use my custom extension interface to create a dedicated memory to share between the CPU and Expedera directly. So perhaps no other agent could access the CPU, but it could make transferring data between the two accelerators, CPU and accelerator, very fast. Remember,
Great.
dedicated bandwidth, dedicated bus.
Great. So we are just about out of time on our webinar today. Thank you for everyone who joined us live, and thank you for those joining us on demand in the future, as it would be. If you have any questions, please feel free to reach out. The questions widget remains active. We will get back to you if we did not get a chance to answer your questions. So thanks, everyone, and have a wonderful day.
Thank you. Have a great day.